Welcome back. We got into the point where we asked, okay, what are unfoldings? So this is now a technique that's been used quite a bit for model checking, but now we want to use it for testing purposes. So here's an example. So here we have a Petri net that you can think of as a system where in the initial state we fork two threads, and then this thread on the left-hand side is going to execute this local instruction, then it's going to do another local instruction, getting back to the initial state, and it will keep on doing this sequence of two instructions forever, while the second forked thread will first do this local thing, then do this other local thing, returning it back to its initial state, and keep doing this forever. Now, if we generate just the execution tree of this Petri net without any partial order reductions now, then what we'll have is basically a tree that's going to grow exponentially, and this is going to go on growing kind of larger by the level. While the unfolding, as you remember, it's going to generate a new copy of this transition with some new states in here, and then it's going to fire this transition, then it's going to fire that transition, which is a copy of that one, and then instead of putting this token back to there, it's actually going to generate a new copy of S2. So if you like, this unfolding is just the unwinding of the Petri net into an acyclic structure. And now the unfolding grows linearly here. So in order to kind of get closer to the unfolding, you should use partial order reduction techniques on the execution tree. Okay, so that's one example. Now, how do we use unfoldings with dynamic symbolic execution? So here's what we do. So we basically use Petri nets to model just the control flow graph and the data flow between threads in a program. Nothing more. So it's a kind of a structure that just contains the control flow and the data flow, and it doesn't have any of the guards. It doesn't have any of the data manipulation things or anything. It's just the structure induced by data flow, control flow, and local branching as well. So if we have so let's see, here we have a trick that we do. So we use a trick called place replication, where a global variable is split into n variables, one for each thread. So for this to work, we actually need to know how many threads in our program we have. We can fix this later on, but for now, let's assume that we start all the threads in the beginning and live with that. So we have, let's say, 4 threads running in the beginning, and then a write of a global variable is basically going to be something which takes the local state of a particular thread that is being executed. So this is both the program counter and all the local state that gets modified. So it modifies the local state producing this, and then it reads all the copies of the global variable, so one for each thread, and then it produces new versions. So here it kind of removes the old versions of the global variable from each one of the threads and produces new versions for each one of the threads. Now, this trick allows us to have reads that only read a local copy of a global variable. So a read will take the program counter and the local state of a thread. It will produce a new program counter and local state modifications. It will take the copy of that thread of the global variable, and it will produce it back without modifying it. Now the lock and unlock are fairly similar. So lock will grab a token from the lock place, and once an unlock event happens later on, it will produce it back. So here's another slide showing the same thing. So basically, we'll have this local copy of each shared variable. So in here we have shared variable x, and it will have n copies. So let's say if we have 4 threads, there will be 4 places in here. And this guy, if it's kind of modifying the global variable of thread 1, then it's just, so if it's reading the global variable in thread 1, then it's just going to grab the thread 1 version of it. So with this, we can get the following. Actually, all reads will be independent in here because they will touch different places, right? Writes will be dependent with reads because in order for write to happen, it has to kind of grab all the old copies of the variable contents and produce all new copies. Okay, so the unfolding shows the control and data flows possible in all different ways to solve data races in Java code. Our tooling doesn't actually explicitly build the Petri net. Our unfolding actually has no data in it, so there's no kind of value in here. This is just that, okay, there's just a black token in here. The contents of the variable x are never stored on the Petri net side. And there are no guards in any of these transitions, so the guards are also handled outside the Petri net's world. So the Petri net's world will only have control flow and data flow, but no real data in it. The unfolding will thus be an over-approximation of the potential executions the program will have. Why an over-approximation? Well, because there will be some guards in the program that will not be executable with any data value. But those guards we will solve during the testing using an SMT solver. So we will actually store outside the unfolding the path constraint of the program, and that will have the data. And if that path constraint says that, okay, you can, by the way, you cannot execute this event, then it cannot be executed with any interleaving hitting that state, and it can actually be dropped from the unfolding, and we'll do that. So we will have an over-approximation stating, okay, these might be executable events, and each time we find one, we ask SMT solver, okay, please find me data values that all guards are satisfiable. And if it says no can do, then we'll just drop that off the unfolding and say, okay, we were over-approximating here too much. So branches that are non-feasible are pruned later on. So here's an example. We have one global variable, x. We have thread 1 that initializes its local variable a with the value of x. If a is greater than 0, then it's going to go to an error branch. Then a thread 2 that will initialize its local variable b using the global variable x. Then if b happens to be 0, then it can actually grab a new input and store it to the global variable x, right? So, okay, so what is the unfolding of this one? Well, in the initial unfolding, there's nothing, and then we can just run a random execution of this program. So let's run a random execution of this program. So so let's see what happened. So in here, in the random execution, it seems like, okay, first we did what? Let's see now. First we did read on the thread 1 side, grabbing the global variable x, and this is the local copy of thread 1 of global variable x. Then what we did is we produced a new version of it. Remember that this doesn't go back, but there's a new copy generated each time. Then what happened is that, okay, it seems that we have then run this thread forward one clock cycle, if you like, reading the global variable x again. It will read the local version of it. It will produce a new version in here. And then at this stage, we actually ended up running this this branching here. And actually, in this case, because x was initially 0 and nobody has assigned to it, b actually happens to be 0. And then we hit the then branch, and we actually write the variable x with some value. And the variable x writing requires to grab both copies of the variable x and releases both copies and produces new ones. And okay, so we here's a test run, and this just says that, okay, this guy did this. So this black part is just the control flow. This black part is the control flow of thread 2. And then the data flow, well, it flew in such a way that there were these 2 reads that were first done, and once they were done, then the write was done after that, and then we produced new outputs for the write. And note that in here there's no data. It's just that, okay, this was just how the data flew from thread 1 to thread 2, right? Okay. And now, what can we see from this thing? First of all, we can, just staring at this, we can notice that these 2 reads are concurrent. Why? Because actually in this underlying Petri net they are concurrent. They are also happening in fully disjoint parts of the system. So this read is happening and modifying these 4 places that are in this part of the system. This read is modifying these 4 places that are in this part of the system, and there's no way for them to communicate with each other. So these 2 guys are fully concurrent with each other. We can see that by just staring at the picture, right? We can also see that, that there seems to be a race condition. Why do we see that? Well, we see that, okay, there's actually a read happening here, followed by a write, and it seems that this write actually could also have happened before this read ever happening. So we know that we could actually have written already before this, because this the value of x in here already existed before this. So we know that, okay, we actually could have done the race in another order. So this is similar to the DPOR algorithm figuring out, oh, there's a race between the write and read, and we can figure it out here as well. Okay, there's a race between this read and this write, and we should try the other order as well, right? So let's add the other order. So that will be of course, the execution. You can see it in the program that, okay, it's the execution where thread 2 is first run until bottom. So it will first do a read, then do a write. So it will grab the initial state of x, and only after this write will the read be possible. And then you can say that, okay, if you do this write, then there will be a new copy of the data, and then there will be another read that grabs that copy, and this place may be better would be down there to denote that this happens later on in the time. So here's so this was the first way of solving the race, and then first write and then read is the other way. And then if we ever hit here, then we also have this if then else in here that can happen, because then after that, after we've written with this one, we no longer know that a is 0 in here, but actually we have to branch. And that's the program. So those are all the possible interleavings this program has. And some of these are now, you could annotate this now with the guards and with the data values, but this is what our algorithm will do on the fly. So it will do things like, okay, you say that, okay, I actually say that this thing can be executable. Then the algorithm will figure out that, okay, you have to then execute this guy. And in order to execute that guy, you have to actually execute that guy and that guy. So that gives us a path constraint. Please fire that, followed by that, followed by that, followed by that. And then we ask, okay, is this guard executable or not? And it actually happens to be executable. So we don't drop it from the unfolding. Yeah, question?
How do you interpret the timing of this from this diagram? I mean, how do you see when the write affects the read in the other thread?
So this write affects that read because there's an arc saying that, okay, this happens before that one.
The line through circle was a local variable.
Yeah.
So, but according to that arrow, the thread 2 is writing to the local variable of thread 1.
No, this is a global variable x. This is the local copy of global variable x for thread 1.
But do you mean local? So it's if the global variable is rewritten, then immediately the local copy is rewritten as well.
Yeah. See, here's a write. So this is the trick that we've been playing. So instead of the write modifying a single variable, it actually atomically modifies two different variables.
Okay.
It modifies the local copy of thread 1, and it atomically also modifies the local copy of thread 2 in here. And that's a trick of the trade. So you can you can do this, and with that you can actually get the fact that this guy that is only reading the local variable actually is independent with this guy who is also reading the global variable, but because they are reading their own local copies, you can actually see that these two things commute and they can be fired in parallel if you like, or in any order in the initial state.
Okay.
So this read in here in this first line.
But so what is the idea of creating local copies of the? Is it just for representation? Can we understand the graph better, or is it for
It is for efficiency reasons. We will have less, if we would just have one copy, we would have more test cases because we would have to try these reads in all different orders, so in both orders. This is like in the DPOR algorithm I was saying, if you would put only one copy, then reads would be like writes. And you would have to try out both orders. Okay, does this read of thread 1 happen first or read of thread 2 happen first? I'm not sure if that clarified things. Yeah?
Semantics of write is in such a way that if you write to a global variable, the local copies will get updated.
Yeah, so all the writes will grab both copies. So this write in here will grab this local copy and that local copy.
This contradicts the notion of global and local variables.
In which sense?
in the sense that a thread can write on a variable, a local variable on another thread.
Well, it's a local copy. I could say all variables are global. But that's kind of it.
But it doesn't contradict. It doesn't matter. So semantics of Java, it doesn't contradict anything.
No.
Okay.
No. So. Yeah.
Local copies are your, say, invention.
Yeah.
That's really local copies. These are just global variables which are represented as several local copies.
Yeah, but they mean something probably in the graph over there. But
So you can, if you insist, you can do let's say a C compiler that each time there's a global variable access. If it's a read, then it locks its local version, does a read of the local version, and then releases it. This C compiler doesn't make any sense, by the way, but you could do it.
So, let me ask like this. So why don't you just create one? Since if you write to a global variable, then a lot of other variables will immediately also be updated with this value. So instead of having like 3 different circles for the same variable, why don't you just put one in the diagram?
Yeah, if I would put one in here, then I would have to, okay, if I would only have one of these guys here.
So instead of having like...
Let's say I kill this one, and then I draw an arc from here to there.
Yeah.
But then I would have to try out both firing this first and then that first, or firing that one first and then this first. So I would have a case analysis of 2 different test cases, while in here I just have a 1 test case, right?
Okay, so you could not describe the different scenarios if you wouldn't have
Yeah. So just consider these 2 guys on their own. I need only 1 test case to test these two guys in this setup. But if I would have an edge from here to here, then I would need 2 test cases.
Okay.
So by doing this trick, I've saved 1 test case, and this multiplies over and over again in my testing trees. Okay.
Oh, perfect.
Okay. Cool. Yeah.
I think that the easiest way in that is that if you don't model the global variable by several local ones, you cannot really model independence between the reads.
Yeah.
In fact, if you only have 1 condition, 1 circle, okay, the 2 reads are going to be in a race.
Yeah.
Always.
Yeah. So it's like, okay, each one of my reads actually modifies the global variable, which is kind of, so, yeah. Okay, so I hope you have gotten some intuition on. Okay, cool. Let's go forward. So this was the whole thing. And as I said, yeah. Now this is how we build these things. So let's do another example. So let's see what this is. This is slightly more complicated, but I don't think there was anything that deep in here. So here we have a global variable x, and then I1 is an input, then I1 gets incremented locally. Then if it happens to be 5, then we assign the global variable. Otherwise, we read the global variable to a local variable copy, and then there's another thread, etc. We read an input, then we read the global variable. If the input happens to be something, then we actually assign a local variable, etc. So nothing really deep. If you represent that as a Petri net, then you'll have these 2 copies once more. This is the thread 1 copy of this global variable x. This is the thread 2 copy of the global variable x. This is the control flow of thread 1 going in here. Now there's actually the data is added in here, but it's not really considered by the unfolding algorithm, but it's here for reference. Then there's a read in here. The global variable x is read, so it's grabbing a token and giving it back. Here x is assigned, so both copies, so both the local thread 1 copy and thread 2 copy are grabbed and returned, and similarly here, etc. So this is how it looks like a Petri net, and when you unfold it, whenever you fire some transition, you make a fresh new copy of the place for the output places. And if you unfold it, then you get this mess down here. So these are usually not human readable. These are for the machine to go through, right? But it has all the ways that the data can flow. So this version of the initial state of the variable x can be read by thread 1 through here, or it can be written here or here, etc., etc. So it has all the data flow that can happen between the threads, plus the control branching. So let's get back to this, this example we already had before. So we had this example where the DPOR test set will always be exponential. So, so we had these n variables, so variable x, and for variable x we have one reading version and one writing variable, and there will be a race on x which one of these threads goes first. And then for variable y we have similarly reading of y and writing of y, and there's a race there. So just a recap, we had this example before. Now if we do the unfolding, it's not pretty, but it is linear size. So this is doing the races between thread 1 and thread 2. Either the read goes first and then the write on the thread 2, or the write goes first, after which the read happens on thread 1 side, right? And for a variable y, either the reading thread 3 goes first and then the write happens, or the writing thread goes first, grabs these, and then the read happens, right? So now in here, if you add more variables, then this unfolding will just grow in width, but not in depth, right? And now if we want to generate a test case that will fire a set of test cases that will fire all the transitions of this unfolding, we can first generate one test case that fires all the reads first, and then fire another test case that fires all the writes first. And with these two test cases, you can cover all the reachable states and all the reachable control flow locations of this program, right? And this shows that this thing that we've been computing can be exponentially more compact than any partial order reduction method that preserves all Mazurkiewicz traces. So, yeah.
I don't see how you discard from there the fact that you can do. So I
Yep.
see this net as two parts. In one you have the x variable, and the other the part
Yep.
comes in the
Yep.
y variable.
Yep.
How do you exclude doing read in one side and write in the other?
Okay. So we can exclude it in that way that we know that there's no communication going on between these parts. These parts are completely disjoint from each other. So we can actually do a case analysis separately for each one of these disjoint parts. And if we do the case analysis saying, okay, in the first test case, let's do the case analysis in the first part by going left, and also in the second part going left, and the third part going left, and the fourth part.
You can see that you may have different files, but the reachable margin and the error are always the same.
No, it's kind of, what I know is that these are all the enabled transitions. If I project this to the original Java program, I know that all the reachable program locations are in this unfolding, if and only if they are reachable. And I can, with two test cases, do a test case that goes through all reachable local control flow locations. So with two test cases, you can cover all assertions that concern local variables. Okay? Other questions? So we lost something. So we've lost actually the deadlocks. So this thing has an exponential number of deadlocks. But now I have something linear, so there's no way the deadlocks are there, right? So the deadlocks actually are there, but they're in symbolic form. So the deadlocks, if you want to recover the deadlocks, you can recover them, but you need an NP solver, like a SAT solver, to enumerate all of them for you. So this is a symbolic representation from which you can check and generate all the deadlocks if you like, but that will take you some time. But now, if a control flow location is listed in here somewhere, then it's reachable. If it's not listed here, then it's unreachable. Right. Questions? Okay. So, as said, the unfolding preserves the reachability of local states, and it preserves the executability of statements. So if a line of code is executable in your program, then there will be one of these events here that will be that line of code, if and only if it's executable, right? Thus, asserts, which are also statements, are checkable. As said, reachability of deadlocks is symbolic, and this is the feature of the thing. So if it would be explicit, we would be as big as DPOR, right? Because it's symbolic in there, we can be more compact. And checking any global state reachability question can be done in NP in the unfolding size using a set solver. And we actually have an SMT solver implementation that can check any global reachability using these unfoldings. So if you like, this thing is a symbolic representation of the program's reachable state space. So we're into the model checking territory in here using testing, which is kind of weird, but still. Okay. So, but I'm kind of skipped over the details on how can we actually generate this thing. So I already warned you that this is not going to be cheap. So going for more compact representations means that the algorithms we run are going to be more expensive. So let's go to this. So this is the unfolding-based testing algorithm. This is from a draft from Kari's thesis. So it's not too difficult. So you start with an initial unfolding that's empty. You look for events enabled in the initial state. While you have something you can add to the unfolding, so like in here we knew that there's this race and this right in here can be added to the unfolding. As long as we know that there are such things, we pick one of them. If that is not in the unfolding, then we figure out, okay, what is the actual concrete execution to get us to execute that state, and we figure also out whether that is actually kind of executable as far as the guards are concerned. Then we go through the statement sequence, figure out for each event if it's not in the unfolding. So if it's something new we haven't seen before, then we add the event to the unfolding. We remove that we don't go through it again in this while loop. So we actually do terminate eventually. And then what we add next is we call this subroutine possible extensions, which is okay. It is giving us, okay, what other things could be added to the unfolding, giving the information we know so far. And now, the truth is this is very expensive. But we've done it, we've micro-optimized it quite a bit, but it's still more expensive than your traditional testing algorithm. So, okay, so the bad news first. So this subroutine in here, this guy who gets called in the innermost loop, it is actually NP complete. So there's an NP routine in the innermost loop of the testing algorithm now. Okay, it is possible to use existing backtracking search algorithms. So you can basically use all the same routines as the unfolding-based Petri net model checkers will use. But if you do that, you'll be way too slow to compete in this domain. So what Kari did was do a kind of special case algorithm for the systems we'll see in this domain. And it's actually possible to do better in practice. So let me show what's the problem here. Okay, and the way why it works better is because we have a specialized structure. The Petri nets we have actually have these places that are always marked. So the token never leaves from here. So if we go in, like in here, this is a funny looking Petri net because that place will always have a token, right? And we actually use this special structure in the algorithms we use for the possible extensions. But let's show the NP hardness. So consider these three SAT formula, x1 or x2 or x3 and not x1 or not x2 or not x3 and not x1 or not x3 or not x2 or not x3. You can generate such a Petri net in such a way that there will be a token in here in some reachable marking if and only if this thing is satisfiable. And now you can do a Java program, multi-threaded Java program that does the same thing. That's left as an exercise to the reader. But yeah, you can do this same thing with a Java program. Now, when you unfold this guy, this is what you'll get at some point. So you'll get such a thing, and now the question is, okay, can I add this t down here? And you can add the t down here if and only if this unfolding is, you can add a t down here if and only if this original net and this formula has a satisfying truth assignment. So the bad news is yeah, there's an NP-hard search algorithm in the core of this. Now, this algorithm is actually polynomial if you fix the maximum synchronization depth of threads. So if you only allow two-way synchronization, this algorithm actually becomes, I think it's quadratic, if I remember correctly.
What does two-way synchronization mean?
So if you would, let's say, if we would disallow normal global variables, but only allow two threads to handshake, only allow two thread handshakes, then this would become polynomial. But if you allow like arbitrary number of threads to, let's say, access a global variable, you can actually implement this thing in Java. Yeah, so that's the bad news. The good news is we don't see this blowing up in our threads. So it seems to work pretty good. So now, okay, let me come back to, let's say, comparing this to the DPOR stuff.
Sorry, you said it doesn't blow up. Is it because in most practical cases you don't have n-way synchronization, or is there any?
In most practical cases, we don't see 3SAT being encoded into Java. But if you would, then it would certainly blow up in our case. So the synchronization patterns seem to be less tricky than arbitrary 3SAT stuff.
So there is more to it than just n-way synchronization. There's also a kind of...
There's kind of theoretical complexity and practical runtime, and how much do they differ. So we're not seeing in practical runtime blow up. That is to say, I can guarantee we
we can generate Java programs out of 3 SAT that will be very hard for output. But they will be hard for DPOR as well. I'm sure of that. But they will just blow up in a different way. For DPOR there will be lots of test cases. For us there will be a very, very compact thing, but when the algorithm hits this stage, it will just start to consume a lot of time trying to figure out, okay, what is the next thing we can do. With DPOR, it's going to go and try out all the interleavings and people back. So it's like, yeah, we get more compact things, and because of that, we can sometimes, but yeah. Okay, so I don't know. In practice, we seem to be working pretty good. So as said, as already said, this DPOR depends on the order in which you do things. Here's one example. I already showed another one. But yeah, that's the same idea here that, okay, the optimal reduction would have two global states, but we see 3. But this unfolding approach is actually canonical. So for a given program, there's one canonic unfolding. So it always gives the same output, no matter how you do it. So this approach is computationally more expensive per test run than DPOR. Okay. Okay. So batteries are out. Okay. Let me take a sip.
Okay. So what do you think? Does it work? Okay, cool. So yeah. So what's nice is we can have reductions in number of test runs that can be exponential. And I already talked about this a lot. This approach is very useful for programs where the control depends heavily on input values, where DPOR might explore large subtrees. As said, dynamic thread creation wasn't easy. We actually have another paper that improves on this. So this was our first paper from 2012. We've done some more stuff. So this is something that's coming out in ACSD in, I think, what is it, a couple of weeks? Yeah. So we can also use even more compact symbolic representations. They're called contextual nets. And here we'll get rid of the place duplication stuff and do something else. We'll use so-called read arcs. So we'll have a specialized formalism that can kind of handle reads in a special way. A read arc requires a token to be present in order for a transition to fire, but firing it doesn't consume a token. And we'll get even more compact representations, and actually I noticed that we're sometimes getting exponential improvements using this new technique over the original one. Computing potential extensions becomes more demanding in practice. It's still in NP, but in practice it's more difficult. So here's the example I showed you. So what can we do to get rid of the place duplication? So let's do a place duplication removal. And what we now have is one place per global variable where actually we have these undirected arcs in here, which are called read arcs, that reads require in here. So in order for this read to be enabled, this place has to have a token, and when this read is fired, that place will remain to have a token, but we move in here. And similarly, now with this read, so this will also be enabled whenever there's a token there, and it will put the token there. Now, and similarly, there's a read from here to there. Notice that the writes still consume a token, so they basically generate new values. So this write might be, and actually is in this case, the write will destroy the old contents of the global variable x and replace it with a new one, new content, so it will actually have to be modeled in here. So now in this model, this class of Petri nets is a bit subtle. So there's things like, okay, let's move forward. But let's say these are much more readable. But truly understanding what does this mean is more tricky. Okay, here's another example. So let's suppose that we have a thread that is trying to write a global variable x, and other two threads that are trying to read it. Now, if we think about all the scenarios in our original place replication encoding, how many writes will there be? Well, there will be one write where the write happens immediately at the beginning, one write where the write happens after thread 2 has read it, but thread 3 hasn't, one write where thread 3 has read it, but thread 2 hasn't, and one write where both of the reads have happened, but the write hasn't happened yet. So there will be 4 cases of interleaving these two reads with a write, basically. And now if we move to the place to the read arcs world, this is what this thing will look like. So there will be a write in here, which will grab the initial state and produce the new state. And then there will be a read, which is enabled if and only if the write hasn't already happened, and another read that's enabled if the write hasn't already happened, and then this other read, which is enabled if and only if this write has already happened. So with this, if you add the number of readers, you add 3 readers, 4 readers, 5 readers, you will have, in this world, you will have, 4, 8, 16 different cases to consider in here, while in this world, you will have just 2 cases, right? And now, you can run 2 test cases through this program and test all the local state reachability properties, right? One where the write happens first and then all the reads, and one where the read happens first and then all the writes, right? And that's all there is as far as case analysis goes. This is almost the same example. This is from Kari's thesis once more. We added one more thread in parallel that doesn't communicate with these guys at all. It actually does only local computation. And then we have now all the arcs for your pleasure. So how many arcs are there? So this is the original net when you drew all the arcs. And then there's this other guy who does something completely isolated from the others. And then if you do the same thing with the read arcs, this is slightly different notation with, but anyhow, you'll have something like this. Okay. Now coming back to the subtlety of how these things are then subtle, Here's an example of a program which has a global variable x, then we're assigning 5 to it, and then we're reading it, then another thread reads an input, compares that to 0, and then reads x to local variable c, and then reads x to local variable d. And if we do the unfolding algorithm with this, then we can do things like, okay, this execution order is impossible, so if we fire first this write, then we can no longer actually do this read because this token has been consumed. Okay, and this is even more subtle, so here's another example. So I'm claiming here that R3 and R5 can never be actually fired together in any test execution. Why is that? Well, because in order to fire this read, you have to fire this write because these are from the same thread. In order to, so let's see. So this has to be there.
You consume X, that prevents R5.
Sorry?
If you fire WD2,
Yeah.
you consume X, and then you cannot.
Okay. There's. Let's see if I have a bug here. Okay, let's see now. W2 has to become before. Now I'm losing it. Okay, so let's see. So this has to happen before this guy. Yeah, because these are in the same thread, right? This guy has to be fired before this guy because this is reading something, and this write will destroy that variable, right? Then this write has to happen before this read because there's a control flow dependency, so this thing in the same thread can only happen after this guy. And now this guy has to happen before that one because if that would fire first, then this thing would be there already. So there's a cycle of things which says that, okay, actually you cannot ever fire W2, R3, W4, and R5 together at the same time. And these cycles can be arbitrarily large. So just because you get smaller systems, you get more complexity in analyzing them. Of course, a SAT checker will easily check whether there's cycles or not, or any backtracking search, but it's just saying that these things get very tricky to understand. Okay, so contextual nets are sometimes much more compact. They can be exponentially more compact, have less test runs, have more complex theory, actually are very subtle, as we found out just. Take a while to figure out. Algorithms are more complex. Dynamic thread creation is actually easy now with these guys. So here's some experimental data. So how do these algorithms actually compare to different things? So this is actually, the DPOR in here is actually our own implementation, and it's actually, I would say, pretty good. This is now Kari's new tool that is newer than LCT. It's not released yet. This is the number of test cases we get. This is with the basic unfolding method, and this is with DPOR. So if we generate the same number of test cases in here, we're like 4 times slower. Sometimes we're able to generate 3 test cases when DPOR goes to 2,000. Sometimes the test cases are fairly similar. Usually then DPOR beats us, but not by much. Yeah. Then what else? Then here we're pretty similar, but because we're like 4 times smaller, or 3 times smaller, we're actually better. So even though we have an NP solver in the innermost loop, we're still able to do things. If we add the read arcs into the setup, we can sometimes generate 5 times less test cases. In here, we're able to generate also 5 times less. So usually things are actually very competitive. When it doesn't help, it slows things down, like here from 2.5 minutes to 3.5 minutes. So adding the read arcs makes things slower, but it's getting us smaller test suites. Okay, let's see. Summary for this part, I still have slides. So how much time do I have? 5 minutes. Okay, let me put that there. So 5 minutes. So then I'll skip some of the advanced stuff at the end. Summary. So this is a new approach for multi-threaded program testing. It is quite efficient actually, but it required a lot of tweaking to get that fast. If you do just naive textbook things, it will not be this fast. It can generate exponentially smaller test suites than persistent set algorithms. Global state reachability is more complex, so we use SMT solvers to actually check for global state reachability properties. Also, we have some specialized algorithms for things like deadlock checking that are backtrack searches on unfoldings. Now, there's another paper we just got into TAP 2014 that I'll talk about for 4 minutes, then I'll close. We had an approach that where we actually start to do so-called state matching. So we try to figure out when we've seen the same state in different paths of the program. Now this is very tricky if we have data manipulation. But we thought, okay, what can be done if we do not use an SMT solver here? So our solution is, well, let's see the motivating example. So here's the motivating example. So we have this program where we have one lock and 2 threads are grabbing that lock, modifying a different variable each, and releasing that lock. That happens in many programs. So you have an array, and there's a global lock protecting that array, and threads are going to go and modify different things in there. Now, we know that these 2 interleavings will result in the same final state, even though these are fully dependent on each other. So we can come up with something called lightweight state matching in such a way that we do an abstraction of the system such that if that abstraction reaches a state M in 2 different branches of the test suite, if those states are equivalent in the abstraction, then the symbolic states are also equivalent, but not the other way around. It might be that symbolic states are equivalent, but we might need an SMT solver to figure that out. So this is like, okay, sometimes we can cut, but we do not guarantee you to cut. Okay, so let me show you the way how we do this. So this is our abstraction. So from the program, we do the locking as follows. So we have one place for the lock. So this is what you've seen already before. So we unlock things. For reads, we actually know that the read doesn't modify the local variable. So we actually return the value of the read. And also this lock-unlock sequence doesn't modify the contents of the lock. So we return this guy back. Now writes modify this contents of this variable. So we actually modify the contents of the global variable. Right. And then if we have symbolic branching, we just branch like that. And now we can actually prove that if we in 2 branches, if we project the behavior of the program on this Petri net, and we in 2 branches hit the same Petri net global state, then the states will be the same also on the concrete side. Especially in this locking example, we will basically, this part will modify variable x, this one will modify variable y, and then the lock will be returned, and no matter which route we took, we end up in the exact same marking on the Petrian side, and therefore we can say, okay, let's not test the other interleaving, we can cut here. Okay, and we added this to just standard naive search. We added this to unfoldings. There's a trick. You have to know unfolding theory, not to do an unsound algorithm. There's something called adequate order on line 7. If you drop that, you'll have something unsound. See our book. There's an example in the slides. But this is what we get as experimental results. And this is my second to last slide. So if we do stateless unfolding, we're actually the fastest in this case where we generate 3 test cases, but otherwise we're usually pretty bad. If we do stateless DPOR, we're once fastest. If we do naive search, which is actually doesn't have any partial order reductions at all, just has this cutting heuristic, we're actually the fastest in many cases. So just having this naive cutting is actually pretty good. And if we have unfoldings plus cutting, then the set of the number of test suites is the smallest, but we're not always the fastest. Quite often the naive way is actually fastest, but might generate more test cases. So summary, this can yield dramatic reductions. It's very simple technique, very easy to implement. Naive state matching beats DPOR and all the tricky partial order reductions in often. So, and adding this to DPOR is straightforward future work. And, but adding this to the unfoldings actually is very tricky, theory-wise. So, okay, so after this slide I'll stop. Sorry, I forgot this slide. So, when testing multi-thread programs, partial order reduction should be used, is my thing. They combine nicely with dynamic symbolic execution. You can take a look at our papers if you want to implement DPOR. It should be easy to implement based on those. Unfoldings are exponentially more compact than DPOR, but you need more complex theory and algorithms, so that's more work. State matching seems to be essential for performance, and we're kind of exploring the border between testing and model checking, because many of our techniques can actually prove that there are unreachable things. So we're actually fairly close to model checking already. Okay, that's it. Thank you.